It's a pleasure to have with us Juan Carrasquilla from the Vector Institute. Juan, thanks for accepting the invitation. And Juan will be talking about neural autoregressive models for many-body physics. So Juan, please.
Yes, so thank you so much for the invitation. So yeah, I'm going to try to tell you about how to use autoregressive models for quantum many-body physics. But so usually I try to first explain for why I'd like to, or why I think this is a good idea, right? Like, so why, in general, why use machine learning for quantum physics? And what I typically say or argue is there's a common structure between the problems people deal with in machine learning and the problems we care about in quantum many-body physics. So I guess I'll start with the first aspect that I find appealing is the problem of high dimensionality in quantum mechanics and in machine learning. So, and usually I start with the wave function of a many-body system with, say, n degrees of freedom. And so the idea is that the generic specification of a quantum state requires resources that grow exponentially large in the number of these degrees of freedom. For instance, the wave function, which specifies everything we can know about a quantum state, is a vector with say 2 to the n components. If the degrees of freedom are say spin 1/2 particles or spin 1/2 degrees of freedom, and this growth is what hinders our ability to study the systems, at least computationally, in a way that that today's best supercomputers can only solve the wave equation or the Schrodinger's equation exactly for a systems with up to say 45 spins. Yet technologically relevant problems in chemistry, condensed matter physics, quantum computing, and high energy physics and gauge theories are much larger than say 45 degrees of freedom, and so we have to exploit the structure of the problem to make progress. And so, I guess the key here is that the amount of information in these systems typically is smaller than this maximum capacity or this exponential explosion or this exponential amount of information, so that we have some structure in the problem and we exploit it. And so I have two examples here. So one is quantum Monte Carlo simulations, where we perform a stochastic exploration of the most important regions of this gigantic state space. And this is such that we've made progress on a significant number of problems by using these techniques, by doing these stochastic explorations. Then the other example I have is tensor networks, which are representation of quantum states. What people exploit when they use tensor networks is that many quantum states that are realized in nature have little entanglement. And so you go from a generic specification with, let's say, an exponential amount of parameters in the wave function to a polynomial factorization of the wave function that basically exploits the fact that the states have little entanglement. So both techniques have led to profound implications to our understanding of quantum many-body physics. But then the idea is machine learning, right? Like we're thinking about using machine learning. And so the commonality, again, is the high dimensionality, but also the common structure, the structure that the problems that appear in machine learning. And what I'd like to propose is that both quantum and machine learning problems have a lot of shared structure and symmetry, right? So, and what I'm asking now is, so what are these commonalities, and are they important beyond mere resemblance, what I'm talking about here, right? Like this argument that I'm trying to make here. And so let me try to explore this a little bit more in detail. So about the first point is dimensionality, right? And so I mentioned the dimensionality of the wave function in quantum physics, but now I'm going to mention the dimensionality of the models people use in machine learning. And what I like to argue is that there's language, for instance, in the context of natural language processing, there's machine translation models live in very high dimensional spaces as well. And so I took this example from a paper called Attention is All You Need, there's the basis of the so-called transformer architecture that is very popular in machine learning and natural language processing and computer vision, where like they took they designed this machine translation architecture that is defined on a very large state space. And the state space is basically the vocabulary size to the maximum length of sentences that they can process, right? And so they use a vocabulary size about 8,000 words. So that's this 8,000 here, which is basically what you need to basically comprehend, say, a newspaper article, right? Like, and then the maximum length of the sentence is about 100 words, which is about a paragraph or two. And that gives you a state space, which is of the order of 10 to the 390, okay, which is very large, even compared to the Hilbert space of 45 spins, okay? So that's the first commonality that we're dealing, or both machine learning and quantum many-body physics deal with very large dimensional state spaces. The other one is the commonality in some of the mathematical objects that we study. So for instance, in unsupervised learning, researchers are interested in, for instance, understanding the underlying probability of a data set. So for instance, this is this famous MNIST data set, and where people do unsupervised learning on this data set, they're interested in understanding, for instance, what's the probability of observing some number 8 versus this other number 8, which is, if you want, better written. So then the idea is that you would find higher probability for the well-written 8 typically compared to an 8 like looks like this, for instance. And so that's in machine learning, but for instance, people in statistical mechanics are interested in, say, in the equilibrium properties of a spin system. And so you study, or we use the Boltzmann distribution, right? Like where what this Boltzmann distribution does is to assign probabilities to spin configurations that could be observed in an experiment or in a material. And so these two probability distributions are very similar, right? Like they basically, for a binary MNIST, that they basically a very similar object, right? So establishing or computing probabilities of, say, configurations. And similarly, the wave function, if we're talking about quantum system, so the wave function is, if you want, a generalization of probability where you assign amplitudes instead of assigning probability distributions to a spin configuration in some basis set that describes the system, right? And so that's the third similarity. So it's this statistical and quantum physics are interested in this, like, high dimensional distributions or wave functions. And then the last one that I'm going to discuss quickly is correlations and symmetries, which share a strikingly similar structure. So for instance, there's a lot of work on critical correlations in machine learning. And so here I'd like to highlight this paper from 2013, where they studied the thermodynamics of natural images. And so what they did was to fit sort of like a Boltzmann distribution to a data set of images of the woods, of the forest. And then what they found is that they assigned a temperature to that distribution, and they see that these images, these natural images, behave pretty much like a critical system, okay? And then when they vary temperature of the data set, quote unquote, what they find is that indeed the specific heat has a peak similar to, for instance, to what happens in the icing model near the critical temperature. So that's one more commonality. And so this idea that natural data sets are critical or are exhibit critical behavior is not just in natural images. This has been observed in natural language and natural images, in music, as well as in flocks. So there's this paper where they study starling flocks, where they found that the starling flocks behave critically. And so all these systems, and also quantum and classical systems at critical points exhibit this power law correlations, right? finally, the symmetries, right? Like there's a lot of interesting symmetries that are common both in many body systems in physics and in machine learning. For instance, some systems have translational, rotational, reflection, and other symmetries which make those systems very rich and very common to what we're interested in. And so those are my arguments for why I like to use this architectures and these models to try to study many body physics. So let me just dig a little bit deeper into what are autoregressive models, the specific models that I'm talking about and that I'm going to be using. So they're, I'm going to introduce them in the context of probability, but this term autoregressive originates from time series models and time series literature, where observations from, say, previous time steps are used to predict the value at the current time step. And so I introduced this idea in the context of probability distribution. So we have some probability P of sigma, where sigma is a collection of variables sigma 1 through sigma n. And then we can use the chain rule of probability to decompose this distribution, where like the variables are factorized in this form: probability of sigma 1 times probability of sigma 2 conditioned on sigma 1. Probability of sigma 3 condition on sigma 1, sigma 2, and so on, all the way through probability of sigma n condition on all the variables except sigma n. Okay, and so the autoregressive part is here, like I pointed out with this arrow here, is that to predict the probability of sigma 3, the current time step, you use information about the variables in the previous step, sigma 1 and sigma 2. Okay, so and the idea is that this factorization can characterize any probability distribution over discrete variables, but in a tabular form. But this representation requires exponential resources to represent. And so what probabilistic autoregressive models do is to alleviate this exponential complexity by parameterizing the conditional. So basically you define some function that is basically a parameterized function with parameters theta that specifies all the conditionals. And so that alleviates this exponential explosion. But apart from alleviating the exponential explosion, there's these probabilistic models based on autoregressive property can be exampled exactly, as opposed to using, for instance, Markov chain Monte Carlo, which can be very slow in for some systems. They allow you to compute the probability of a configuration sigma 1 through sigma n fast, as opposed to models that are normalized, where you need to compute the partition function, which can be very expensive. They can encode mean field theories, which is very useful as a starting point when we're dealing with a problem in quantum many body physics or in machine learning. And the other thing we can do is we can impose symmetries and other inductive biases that are useful for dealing with physical as well as with machine learning problems. And so these properties remain true when we're dealing with a representation of the quantum state as well, which I'm going to discuss soon. So what is a canonical example of an autoregressive model is the recurrent neural network, which is among the most popular autoregressive models in the literature in machine learning. And so the recurrent neural network, so the key building block of an RNN, a recurrent neural network, is a recurrent cell here in green, drawn in green. And so the recurrent cell is a nonlinear function which takes input vector Hn, the so-called memory vector or internal vector, as well as the input or the spin configuration or the probability configuration. The parameters of the RNN are given by this parameters W. It's a matrix and a vector or a bias vector B. And because of the recurrent behavior of this function and the dependency that is generated by this recurrent relation, so you compute vector Hn in terms of the vector Hn minus 1. Then this structure that I have here is useful to parameterize this conditionals, right? And so what we do is we take this vector Hn, which depends on all the previous observations and the previous hidden state Hn minus 1. And then we assign or we compute or we apply a softmax function that basically specifies this conditional. All right, so and that's the one key advantage that we basically, because we use this softmax form, we compute this probability, and that probability comes normalized, which means that we can compute the probability amplitude of the configuration in the end. Another key advantage is this sampling of this recurrent neural network is it's very efficient. Because we can sample each conditional independently. And so what we do is we basically compute P1 first, we sample sigma 1, and then we feed the sigma 1 we observed, and we compute sigma 2, probability of sigma 2, we sample it, and compute probability of sigma 3, conditional on sigma 1 and sigma 2, and so on. And so it gives us the possibility to sample exactly the probability distribution encoded by the recurrent neural network. So that's some of the keys. So that was just one prototypical example, but there are many more autoregressive models that are the so-called transformers that are, if you want, the key architecture behind the recent discoveries or recent breakthroughs in natural language processing. I mean, you've probably heard of this GPT models that are very powerful and that have enabled crazy progress in neural machine translation and language generation. There are neural autoregressive density estimators, autoregressive flows, pixel RNNs, wavenets. The list is long, and they're all powerful in their own like a specific way. So, but sorry, I heard. Is there a question?
No, there's not.
No, okay. Sorry about that. So let me go ahead. And so, yeah, what I'm going to be discussing today is, so I'm going to show you a probabilistic formulation of the quantum state and how we can use that formulation to study quantum physics using these models, okay? And then in that context, we're going to show you how to use this probabilistic models to learn quantum states and the quantum dynamics in the form of a quantum circuit. Then I'm going to discuss a little bit like how we can study or define generalization of the recurrent neural network and make them quantum if you want. And then finally, I'm going to show you the idea of so-called variational neural annealing, which is a technique that we introduced to solve optimization. So those, if you want, are just to highlight, or these examples are to highlight the flexibility of the many things we can do. But this is just only 3 examples. There's a lot more that can be done. So let me first explain this probabilistic formulation of quantum mechanics. And this is inspired by this paper by Feynman in 1981. It was actually not a paper, but a speech he gave in 81, where like he discussed simulation physics with computers, both classical and at the time, I mean, quantum computers were not invented, but this, if you want, this talk was one of the main motivations to build quantum computers, right? And so I mean, this paper is about that, like idea of like introducing a quantum computer, but there's a section where he asks, can quantum systems be probabilistically simulated by a classical computer? And then the answer is no. I highlighted here because he concludes that there are difficulties, right? Like either representing the state probabilistically or representing its dynamics in terms of probability distributions. And what he observes is that there's a bunch of plus or minus signs appearing either in the description of the quantum state or in the description of its dynamics. So this, no, this answer is still true today and is fundamentally linked to the notion of quantum speed up in quantum computing, okay? So this is still true, but this whole discussion refers to an exact simulation of quantum dynamics. But the question we asked was, okay, instead of trying to simulate dynamics exactly with probability, can we do it approximately and use machine learning models instead of exact solutions? So that's what that motivates this, right? Like this probabilistic representation of quantum mechanics and its combination with machine learning models, which I will discuss now. So how is a quantum state traditional described? It's usually traditionally described in terms of a density matrix that describes the statistical state of a system in quantum mechanics. Everything we can possibly know about a quantum system is encoded in this object, this density matrix. For one qubit, say one spin, one half, all these quantum states live in the so-called block sphere. But there are alternative representations, right? Like Wigner, like state space Wigner representation, right? Like, so are these useful? That's kind of like the question. And so, like, let me tell you how to represent this quantum states with only probability. So we're going to be using POVMs, positive valued operator. Positive operator valued measures. And the idea is that there's this the so-called Born rule that connects quantum theory with experiments, right? Like, this is the theoretical bedrock that allows us to connect the density matrix of a state, a measurement apparatus, and what you see in the experiment, right? Like, so it's a very important link. And so you take a quantum state rho and you measure it with some POVM, some description of an experimental measurement. And so the relation between the state, the measurement, and the probability of observing an outcome in the measurement A is given by this expression here. And this POVMs, these operators as described, the experimental apparatus are a set of operators M. They're positive semi-definite. And if you sum over all of them, you get the identity operator. So that's, if you want, the description of the experiment. And there is a particular set of POVMs or of measurements that are called informationally complete. And it means that the measurement statistics, meaning this probability distribution, contains all the information about the quantum state. And so pictorially, what this is like, you take a quantum state rho, and you can think of it as a 3D object, and you want to reconstruct this object, right? And so if you want to reconstruct this object, because it's 3D, you should be looking at it from different directions for you to have a high fidelity reconstruction or a high fidelity understanding of what the object looks like, right? And so the same is true in quantum states, except that the states are very high dimensional. And so you have to have this very high dimensional operators that look at the state, right? And so what I mean by informationally complete is a set of measurements that look at this high dimensional state from many, many directions. All right. So, but the most important meaning, at least for our what I'm trying to explain, is that there's measurements as such that the relation between rho and this distribution can be inverted, right? Like, so here we go from rho to the probability distribution. So if the information, if the measurement that you have is informationally complete, you can go from P to rho, okay? And that's what we exploit here. So this is Born rule, so that relation. And so if information is completeness, means that this relation can be inverted. And so that's the math that I won't go into the detail, but it's basically that you can write the quantum state rho in terms of this probability distribution. And everything about quantum mechanics you can do afterwards. You can do unitary evolution, Schrodinger equation, Lindblad equation, measurements, and so on. And so you go, for instance, from this von Neumann, Liouville von Neumann equation, and you can write it in terms of the probability distribution characterized by that characterizes this measurement on the quantum state. And it looks like this just by ensuring you have you are using these informationally complete measurements. So, and the insight we had was, okay, so we have this representation of the quantum state that is probabilistic, and so let's just parameterize these distributions that are very high dimensional with autoregressive models, right? And then try to do quantum mechanics in this space of probabilities and see what happens, right? Like, and then the model, the density matrix, the model becomes just this probabilistic models contracted with some tensors, right? Like, so it's this expression here. It's denser, very simple, and very easy to compute, and so on. So we'll handle all the complexity of the quantum state using just this probabilistic model that comes from, say, machine learning. Okay, that's the idea. So let me give you one example of this program that I set out to carry out. And so it's measurements of a quantum state or learning a quantum state. So this is very similar or almost exactly the same as quantum state tomography. It's just that we're interested in studying very large quantum systems, right? So, and why do we want to go to large systems is because we need to go beyond the standard quantum state tomography that is limited in that the resources that you need to, like the computational resources, are always exponential in standard quantum state tomography. And so the issue is in current experiments in, say, trapped ions, cold atoms, and quantum computers are growing really fast. So 200, 300,000 of quantum degrees of freedom, quantum spins, or cold atoms, and so on. So, and we'd like to try to find techniques to benchmark these experiments as well. And so that's what we wanted to do. So we want to know if our experimental apparatus containing thousands or say hundreds of quantum degrees of freedom is producing the state that the experimental is meant to produce, right? And so to do that, what we do is we prepare that and we assume this state is unknown. I mean, we know something because the experimentalist tells us what it is and what they're trying to do. But what we do is to say verify what they're doing is apply a measurement that probes enough information about the quantum state, that is this informationally complete measurement I was discussing, and we repeat this process, right? Like, so we prepare the state, we measure it, we repeat, measure, repeat, measure, and so on. And so ultimately what we have is a collection of measurements that come from the quantum state. And what we do is we infer a reconstruction of the quantum state raw star, that is this machine learning model contracted with some tensors that account for the phases of the state, right? Because this probability part cannot contain all that information. Yeah, so, and that's the idea that we published in this paper last 2 years. And so here are a couple of examples of doing that. So this is in synthetic numerically generated measurements on a quantum state with 50 spins, and the probability distribution is encoded as a recurrent neural network, a so-called 3-layer GRU. So what we found is we are able to have a very accurate reconstruction of the, or a relatively accurate reconstruction of the quantum state. And here I compare correlation functions, so basically expectation value of the Pauli matrix as a function of the site I. So it's corresponding to a ground state of this Hamiltonian, the so-called transversal Ising model. And so in green, and so in orange is the synthetic state that we use, and in green is this reconstruction using recurrent neural networks. So that we were very happy. So the state is very high dimensional, so you cannot use quantum state tomography to reconstruct it. And then we looked at this, two correlation functions. So expectation value of sigma I, and there's two body correlators, sigma 1 Z, sigma I Z. And they come and they have good agreement. And we looked at this other quantum state, namely the ground state of this so-called Heisenberg Hamiltonian on the triangular lattice. And we went up to a system with 8x8, so about 64 spins. Again, very difficult to reconstruct with standard tomography. And here are the correlations of the synthetic state versus the reconstructed state, which is telling us that these models are capable of describing these quantum states relatively accurately. So that's basically the content of this paper. It has a lot more different states, but that's the gist of it. But then we recently went ahead and did an experimental demonstration using a quantum computer available on the cloud. And this is for producing a so-called GAZ state with 3 qubits. So that's this our reconstruction using so-called, it's a different autoregressive model, so-called transformer architecture. And these are the traditional quantum state tomography. So that was published in this paper. So we were happy that the technique works also experimentally. So, okay, so that was the first example. And that, if you want, is about a system where you have the quantum state you're interested in and you measure it, right? But we wanted a little bit more. So we wanted to explore if we could use these techniques or these models to simulate a slightly much harder, let's say, slightly harder problem, really. So, which is simulation of quantum dynamics. And the system we took a look was a quantum circuit, and we're going to be using again this autoregressive model. So, and as I said, we can do everything in this language of probability. So we started like with learning the quantum state, but you can do real-time dynamics, you can do unitary evolution or Lindblad dynamics, and so on. And so I started with quantum circuit because it was the simplest thing. So what is a quantum circuit and what is quantum computing? Well, what you do is you take an initial state raw, and then you apply a unitary transformation on that state. Then the unitary transformation, if you want, is the quantum circuit or the quantum algorithm you're trying to run on a quantum device. And so we translated this process into this probabilistic language if you want to get quantum mechanics closer to machine learning in some sense, right? And so we applied this Born rule and this inversion. And then this is what we get. So you go from this unitary rotation of the density matrix to basically a matrix multiplication, right? Like, so you take this initial distribution PA corresponding to state rho, and you multiply by this matrix OA, A prime, A double prime. And then you get a time evolved or the unitarily rotated probability distribution, where O obviously depends on the unitary that you applied. Okay, and so that's what we do. So this evolution is almost classical, so very similar to, for instance, what you would do with when you're doing Markov chain Monte Carlo, except this all these matrices are so-called somewhat or quasi-stochastic matrices. And so what it means is that if you sum over the rows of this matrix O A prime A double prime, you get 1 on each row. But the difference between a stochastic matrix is that the entries of this matrix can be positive or negative. So which is what makes simulating quantum mechanics hard, because that implies there's a sign problem in the, if you wanted to do this unitary rotation in this language, right? And so this mathematicians call this somewhat or quasi-stochastic matrices. And so that's what makes it harder, but that doesn't preclude that we can try to simulate approximately this unitary dynamics. Okay, and so what we do is when we apply one gate is we take initial distribution, multiply by this somewhat stochastic matrix, and this results in a time evolved distribution. And so instead of trying to perform this calculation somehow analytically or exactly in some Monte Carlo form, so what we do is we introduce a model P theta that is going to, that we're going to try to fit to this probability distribution, that even though we don't know, we may be able to compute the, say, for instance, the distance between these two. And so what we do is indeed, we introduce a technique using the Kullback-Leibler divergence, which is, if you want, kind of like a measurement between the distance between these two, this probability distributions. And this probability distribution this distance can be computed even though we don't know P U. Okay, so that's what we wrote here. We came up with a way or a technique to compute this distance and to minimize it with respect to the parameters in the model here, P theta. Okay, and so that's the idea that we're gonna be using a probabilistic model, P theta, a recurrent neural network or a transformer to try to fit this PU, right? Like to find a model that gets as close as possible to the time evolved distribution as we can by minimization of the Kullback-Leibler divergence. This quantity here that is only 0 when the two distributions match, or it's always positive otherwise. Okay, So that's the idea. And then we looked at some simple quantum gates, right? Like, so we went ahead and we tried to prepare the so-called G8 set state. That is basically you initialize the quantum state in the 0, 0, 0, a tensor product of 0, 0, 0, 0, and then you start applying Hadamard gate, which is this matrix here, and then this control NOT gates sequentially and this C naught is this matrix here. We also tried this linear graph state where you start again from the same state, apply n, if you have n qubits, you apply n time n the Hadamard matrix again on all the spins, and then control Z, which is this matrix here. They're all unitary, so we can apply this tricks that I was referring to earlier. And so here's what happens when we try this idea. So we measure this Kullback library divergence between these probability distributions as we train the model, right? Like, so this is the time step of the training of the model. And what we see is that this Kullback library divergence decreases initially exponentially fast to very small values of KL divergence. So up to, say, in our numerics, up to 10 to the minus 8, presumably due to the numerical accuracy. And then when we apply the second gate, we see the same behavior, except, so first exponentially fast, but then it saturates. And we cannot improve all that much because there's an accumulation of an error when we from the first step. And so if we keep repeating this process, we will start accumulating errors as we apply more and more unitary matrices. But what we see overall is that behavior in different quantities. So here is the infidelity of the calculation. So basically, infidelity should be 0 if we have a perfect calculation. But what we see is instead it goes down exponentially and then saturates around some small value. And then the error, again, accumulates if you do this procedure some more. And so there's, again, all these figures are telling you the same story, it's just different metrics of the process. And here, so it was only 2 qubits, applying only 2 gates to unitary matrices. And here I have, again, one more example on this small quantum circuit, and only application of just 1 gate, and the story is the same, right? Like that it goes exponentially fast to 0, but it saturates around some point here due to numerical accuracy. These calculations are based on a small transformer, like this transformer architecture, one of these autoregressive models. And this was actually recently published only last week, even though we initially posted the paper on the archive, I think in 2019. So it took some convincing to get it published. Okay. So that's the idea, but finally it's cool that you simulate this tiny circuits, but we wanted to do bigger systems because that was the idea, right? Like, so we went up to 60 qubits, simulating these 2 very simple quantum circuits, and what we found is that the fidelity drops as we make the system bigger and bigger. And it's kind of like the explanation is that error accumulation that I discussed here, that we cannot make this KL go to exactly 0 due to numerical accuracy and perhaps lack of better optimization. But then when you apply the second gate, then you start accumulating error, which decreases the fidelity of the simulation. And so we observe this trend here, right? Like that as we make the system bigger and bigger, the fidelity of the simulation decreases. But on the other hand, if we make the model more powerful, so this is a graph state with a transformer with a number of parameters that is a number. So it depends on the number of hidden dimensions. So if we double it, the fidelity of the simulation improves. So it's this orange line with respect to the green one. And this green line, so I don't have the 2 curves, but it's just a fixed G8 simulation. So, it works, but of course, as you make the system bigger and bigger, you start finding issues, right? Like, or the fidelity decreases, but not dramatically, right? Like, so it's more or less like linear in the number of qubits, at least for this quantum circuits. So let me switch gears and give you, so if you want, what we did was to try to make quantum physics look a little bit like machine learning, right? Like, and then apply machine learning techniques to simulate dynamics and to reconstruct quantum states. But you can also do the opposite, right? Like, so you can take a machine learning architecture or a machine learning idea and try to bring that idea closer to quantum physics, right? And so that's, if you want, the spirit of this. So we took a recurrent neural network and we generalized it so that it looks like a many-body wave function. Okay, so that's, if you want, colloquially what I call bringing ML closer to to quantum physics. Okay, and that's this paper here by my graduate student Mohammed and with my collaborators. And so what we did here was, so we took this idea of a recurrent neural network, and first we said, okay, how about we do kind of like a coherent superposition of the probability distribution encoded by the RNN. So that's one way of defining a wave function. But unfortunately, this wave function needs this.
Hello, everyone.
Hello?
Andre?
Is there a question?
Man, I like your background.
Yeah, it's kind of cool.
Quirky.
Oh, I'm so tired.
I hear it.
When is your
8 a.m. this morning?
You had the lecture. I have a talk on Wednesday, and I'm completely stressed out.
Maybe, okay.
Can I go ahead? I think.
Sorry, yeah, for the interruption. Okay,
awesome.
Please go ahead.
Okay, cool. So yeah, so we defined this this wave function and as a coherent superposition of this probability amplitudes, but it misses critical information. So because wave functions are complex valued, and so what we did was we so on top of computing a probability at each of the conditionals, we also computed like a partial phase of the quantum state at each time step, and then we sum all this up and define a global phase for the wave function. And so that way we define a valid quantum state, okay? And so what we did was we tackled solving ground states of quantum many-body Hamiltonians using this idea, okay? And so we took a look at the transoscillizing model with, say, 1,000 spins, and we found very accurate energies. And we took a look also at a so-called J1, J2 model in 1D, and again, found very accurate representations. We had to do a little bit more work. So we had to encode symmetries in the recurrent neural network. So we used spin inversion symmetry, mirror reflection, and conservation of magnetization in these models to successfully reproduce the ground state of these systems. And here, like just to flash that, or to highlight that the results that we get are really comparable with state-of-the-art density matrix renormalization group calculations. So these are spin-spin correlation functions as a function of the site in the chain. This is for the transoscillizing model. And these are, yes, two-body correlations that what we see is, yeah, they match really, really well with DMRG. And these are entanglement entropies, which again match really well with DMRG, basically highlighting that we can compute these systems very accurately. Okay, so that's it for this topic. And oh, sorry, one more thing is these were all one-dimensional systems, and then we studied again two-dimensional systems. So these recurrent neural networks can be defined basically in any dimension. And what we found out is that they produce some of the best, most accurate results for the ground states of systems in 2D compared to previous techniques, right? Like, so this green is the 2D recurrent neural network. It's the best for the transoscillizing model in 2D, below the critical point, at the critical point, and above the critical point. Although all the other techniques are very accurate as well. Okay, so the last topic I'd like to discuss in my last 5 minutes is the idea of variational neural annealing, again by my student Mohammed. So it's the idea that combinatorial optimization can be solved with recurrent neural networks. And that's the idea is, okay, many challenges in science and technology can be cast as optimization, and these are important in many areas like artificial intelligence, machine learning, software engineering, mathematics, and even computer science. And so there are problems that are interesting, like the traveling salesman problem, nurse scheduling, vehicle routing, factoring, numbers, chip placement, and so on. And so the idea is that so there's a connection between material science and optimization, laid back in the 80s by Kirkpatrick and collaborators, where they use simulated annealing to solve this combinatorial optimization problems. And so what they do is they show that metropolis, like Markov chain Monte Carlo algorithm, can approximate the solution of this combinatorial optimization problems by annealing the temperature of the simulation very slowly. Okay, and so the question, so the idea is, yes, so you do that, like, so you start simulating this energy function defined by the problem you're tackling, and you start exploring this energy landscape using thermal fluctuations induced by the metropolis algorithm, and then you reduce the temperature. That's the idea. And so you hope that these thermal fluctuations allow you to jump around over this configuration space until you find the optimum, okay, which is this configuration sigma. So, and the same idea is used in simulated or in quantum annealing. The idea is that you change thermal fluctuation and you use quantum tunneling instead to tunnel through these barriers in this combinatorial optimization landscape. So, and what we did was ask this question, right? Can we simulate this techniques, simulated annealing and simulated quantum annealing, variationally using recurrent neural networks? Okay, so that was the question. And it's, again, very similar to the problem that I just explained, where we were trying to simulate ground states of many body physics, except now these have some applications that are relevant in practice, right? And the system, the ground state that we're looking for are not quantum, are classical, but nevertheless, very difficult. MP hard problems are in this class. And so we introduced two techniques, one based on classical physics, where what we do is we try to model the Boltzmann distribution, mimicking the simulated annealing process, but instead of the Boltzmann distribution, we use a model P theta. And instead of the exact distribution, as I said, we use a variational principle to optimize the parameters of this model, and then decrease the temperature very slowly. So here, the F is the free energy of the system, the true energy of the system. F theta is the variational free energy of the system, and S is the entropy of the model P theta. And as in simulated annealing, this classical technique from 1983, we decrease the temperature as well, very slowly. Okay, and we also introduce a quantum version of this, where we, instead of using simulated quantum annealing or quantum annealing, we do a variational calculation. And so we promote this RNN to a quantum state using this RNN wave function that I explained. And we use the energy of the quantum Hamiltonian, of this quantum Hamiltonian, instead of this classical free energy. Okay, and where we have this new, okay, we have the target Hamiltonian, which encodes the problem, and we have some driver Hamiltonian that induces this tunneling between minima in the energy landscape induced by this target Hamiltonian. Okay, and then what we do is we slowly decrease the driver Hamiltonian, or the amplitude of the driver Hamiltonian, and then we hope to find the ground state of the target Hamiltonian, of the problem Hamiltonian. So let me skip this, and let me just show you what happens when we tackle two problems. When we tackle the Edwards-Anderson problem, which is this two-dimensional spin glass Hamiltonian, as we tackle this problem with different techniques. So, and I want to focus on figure B for the sake of time, because it's where we compare our variational classical annealing with the techniques that are typically traditional in the combinatorial optimization literature, namely simulated annealing and simulated quantum annealing. And so what we found is that as we make the number of annealing steps longer and longer, what we found is that eventually our variational technique beats both simulated annealing and simulated quantum annealings, which, if you want, gives us an explored tool for combinatorial optimization. The same is true when we do fully connected spin glasses. So these are based on the Sherrington-Kirkpatrick model, which is a classical model of a spin glass. And we find the same behavior. Basically, if we allow enough a very slow decrease of temperature, we find solutions that are of higher quality. And these are other models of fully connected spin glasses where we observe the same. And so let me conclude before I run. I just ran out of time. So we explore this neural autoregressive models for a set of problems in many body physics and on optimization. We explore quantum state reconstruction, simulation of quantum dynamics, in particular quantum circuits. We use recurrent neural network functions and found accurate ground states and a very compact representation of wave functions. And we did this variational annealing where we found that these models produce very accurate solutions to challenging spin glass problems. We have done more, but I'm going to leave it here and apologize for the delay, for the rush at the end.
So thanks a lot. So I guess we have time for a couple of questions. I mean, does anyone have a question? Okay, Kai, can you please unmute and?
Yeah. So thank you, Juan, for your very nice talk. So I just want to hear what's your comments on the fact that those autoregressive neural network models basically need you to have a fixed order of your input variables beforehand. Some people might argue this is non-physical. So what's your opinion on this issue?
Yes, that's a very good question. So this is an arbitrary choice, right? Like it is very natural when you're studying a one-dimensional system, right? Like for instance, we studied this systems here. So these are 1D, and it's a very natural choice, right? Like you order them as you order your spins in the lattice. In 2 dimensions, what we do is, so we select a snake path, and this is a little bit arbitrary, and but we deal with it by just defining it, by just defining how we pass these hidden states, such that we respect the 2-dimensional structure of the lattice, right? But you are right that there's an arbitrary choice on the way you choose the ordering, right? But this is true for many other ansatz, right? Like, so this is true also for a matrix product state, for instance. You have to choose an order, and that's if you want a shortcoming. And what people do and what we do is typically try to find an ordering that respects the physics of the problem as much as possible, but it is always going to be there. That's a good question. Thank you.
Thank you.
Are there more questions? So, yeah.
Yeah, thanks. So my question is about the, you had this result for 50 spins in the Ising model, and then computing the magnetization. And
yeah, so in this tomography? This
one, yeah. So naively, so the Hilbert space should be 2 to the 50, say, size of the Hilbert space. So is there a way you can characterize how big the space is that you explore here? Say, is it smaller than the entire Hilbert space?
Yes, so it's that's right. So it has, okay, so I cannot tell you how big, so I can tell you how many parameters our model has, right? So it has about 200 parameters, right? So it's if you want, in terms of so yeah, that's, yeah, so in terms, in the sense that it's a number that is much smaller than 2 to the 50 in terms of, like, yes, the number of parameters that you would need to describe the ground state of this system exactly. And about the size of the state space that I explore, I'm not sure I know how to characterize this more precisely.
Yeah, so I guess my question is there things that you can't describe, or that you with a POVM, is there kind of a proof that you can still describe everything, so to speak?
So the POVM that we use is capable of, I mean, it forms a basis for density matrices. Okay, it forms a basis for density matrices in this space for 50 spins, right? Like, so we can define it for any number of spins, and so you could represent any state there, but the probability distribution that we use can only represent a fraction, like a tiny, like a measure, a zero measure, I mean, region of that state space, right? Like, because it only has around 200 parameters, right? Like, so you can only visit a tiny slice of that, huge space. But what I was saying is that these models are structured in a kind of like a physically reasonable way because of that commonalities that I was arguing, that even if you can describe only a tiny slice, this slice is not too far from the states that are interesting, at least from this that we have explored, right? I don't know if this answered the question, but
yeah, no, thanks, interesting. Yeah.
Thank you.
So are there more questions? So since there are no more questions, let's thank Juan again.
Thank you so much, everybody.
Thanks.